Everyone, this is lesson 11 of the Particles and Energy scheme of work on heating and cooling, and it comes after a sequence of lessons where we've looked at the concept of temperature. And by this point, I would hope that your students are pretty comfortable with the idea that the temperature of a substance depends on the average kinetic energy of the particles. So if there's lots of kinetic energy in the particles, then the object is at a higher temperature, or vice versa. For an object at a lower temperature, that means there's not so much kinetic energy in the particles. And we saw all sorts of examples and drew all sorts of diagrams to illustrate that concept. Now what we've got here is something slightly different, and it's something students get confused about a lot, the difference between temperature and heating. And I think what we want to emphasize to students is heating is a form of energy transfer, whereas temperature is a measure of effectively an energy store, and that distinction is quite useful. So the way I illustrate this is just with a concrete example, and it's something that in the latter part of this lesson, in the kind of deliberate practice phase, I want them to be able to explain. And that is, why is it that if you take a nice cold can of Coke out of the fridge and just leave it in your kitchen or wherever at room temperature, why does that can of Coke warm up? And it's a nice illustration of how heating happens, and also another really important idea, which is thermal equilibrium. So when I'm asking students to explain things, I tend to draw things in a grid, and let me show you what I mean by that. So the first thing I'm going to do is look at one case, which is when the can of Coke is inside the fridge. So I'm going to draw my fridge here. I'm going to draw my can of Coke in here. It's a bit of an empty fridge, but it'll do for now. And what I'm going to state to the students is the air inside this fridge is going to be nice and cool, right down towards the freezing point of water. Obviously not below the freezing point of water, that would be a freezer, not a fridge. So I'm going to say it's about 3 degrees C. And what I'm going to do is zoom in on here and have a look what's going on in terms of the interaction between my can of Coke and the air inside the fridge. So when I zoom in here like this and draw this box to show what's going on at the micro level, because remember, as scientists, what we're trying to do is explain what's going on at the macro level, what we can see, in terms of things at the micro level, things that we can't see. So I'm going to draw the edge of my can of Coke here, and I'm going to draw the particles in my solid can, just like this. I'm not too worried at this stage about what's going on in the liquid Coke. I'm just worried about I can just draw the can for the time being. Now that does lead to something students find quite tricky, but we'll come back to that in a minute. And what I want to emphasize to students is that because the particles are, or because the can is solid, the particles in the can are arranged in this fixed lattice, and they're just vibrating on the spot which I draw like that. Now, obviously, not all of the particles will be vibrating at the same rate, because some will have a little bit more kinetic energy, so some might be vibrating a little bit more, and some might have a little bit less. So I can sketch that one like that as well. Now, when I look at the particles in the air inside the fridge, what I'm going to see here is that I'm just going to draw a few over here for now. On average, they're going to have quite a low kinetic energy. And the reason for that is because the air is quite cold. Now, obviously, I'm exaggerating. This is a schematic diagram, but what I want to show here is that they don't have loads and loads and loads of kinetic energy. Now, what I want to do is illustrate to the students that actually these two objects inside here, they're going to be at the same temperature. So let's put same temperature. And we'll explain the reason for this. But at the moment, I just want to make it clear to them that means they have the same average kinetic energy, or KE, like that. And what this means is that for every particle in here that collides with another, so let's take a particle like this, let's draw an air particle here, that's got a bit more kinetic energy like that, what this is going to do, this is going to collide with this particle in the metal and make it vibrate a bit more. It's going to give a bit more kinetic energy to the particles in the can. But what that does, as a consequence, is means this particle here now has a bit less kinetic energy. So this is what's going on. Some of the particles are going to have more kinetic energy in the air. They're going to collide, and this is the first time we've introduced the word collide, so it might be worth us writing this down. Let's make a note of that here. They're going to collide, which means bounce, and you can explicitly teach that to the students. They're going to collide with the particles in the can. That's going to cause the particles in the can to vibrate a bit more, and therefore this is going to have a bit less kinetic energy. But for every one of those that's going to give some kinetic energy to the particles in the can, there's going to be another one here, which I'll draw here like this, which is going super slowly. Because it's quite cold air, you'll have some that are moving very, very slowly indeed. Now this will collide with this faster moving, or it's not really moving, this particle that's vibrating more vigorously. We might use that word vigorously. And what that's going to do, this is going to give it a bit of a bump of energy, so this one's going to move away a bit faster. But what that means is, if I get rid of this particle here is going to move a bit less vigorously. It's going to vibrate not as much as it was before, so it's going to lose some kinetic energy. Now what I want the idea that I want to get across to students is that the rate of energy transferred from the can to the air is going to be exactly the same as the rate of energy transferred from the air to the can. So I might write that down like this. I might write energy from can to air is equal to the energy from air to can. Now, this is year 7. I'm not talking about rate of energy transfer or anything like that. I'm kind of glossing it a little bit. But the idea that I want to get across is this is called thermal equilibrium. And this is why the two stay at the same temperature, because for every particle from the air that is giving energy or kinetic energy to the particles in the can, there's a particle in the can that's going to give kinetic energy to the particles in the air. And this is quite a tricky concept, but I think it's worth showing students this, because then it's going to make the process of heating and cooling that we'll see very shortly a bit clearer. So this is what's going on in here inside the fridge, is that you've got an equal rate of energy transfer back and forth, hence the two are in thermal equilibrium, they're both at the same temperature. Now what I'm going to do next is draw a table like this, and now I'm going to tell students that I've taken my can of Coke out from the fridge and I've put it onto the table just out in the kitchen, which is at room temperature. So I'm going to say this is 23 degrees C, quite a warm room. So what I want students to understand now is, how is the process different at this temperature compared to inside the fridge at the lower temperature? What I'm going to do, I'm going to zoom in again like this. And hopefully what you see here, firstly, I always move from concrete to abstract, so from what's going on at the macro level that we can see to the micro level that we can't see. And this grid method is really nice to have kind of concrete to abstract in one case and concrete to abstract in another case, because it really illustrates the difference. And laying your diagrams out like that will really help students explain it in depth, because they'll see exactly what's going on. So I'm going to now sketch my particles here. For the sake of time, I'm not going to sketch the second row, but I'm going to show here that these, because the can is still going to be at 3 degrees C, 3 degrees C, these are going to be jiggling just like the ones that we saw before. So there might be the odd one which is jiggling a bit more, but in general they're not jiggling that much. Okay. But what I want to show here is that actually the air particles in the air outside of the fridge, on average, are going to have a higher kinetic energy than the air particles that were inside the fridge. And the reason for this is the air outside the fridge is at a higher temperature. So what I'm going to do is draw a few just over here like this and show them with longer arrows like that. And then I'm going to say, well, okay, if on average they all have quite a bit more energy, then actually most of the particles, when they collide with particles from the can, actually what they're going to do on average is they're going to bump into the particle in the can, they're going to make it vibrate a bit more, so I'll show some more vibrations there, and they're going to lose a bit of energy like that. And instead of there being one slower moving particle for every faster moving particle like we saw in the fridge, actually on average there's a lot more faster moving particles, so they're going to keep bumping into the particles in the can. They'll lose energy in the process, but what that means is the average kinetic energy of the particles in the can is going to increase. So I might note here that here the particles in the air have a higher temperature. Sorry, the air has a higher temperature. That's a misconception there, isn't it? The air has a higher temperature, which means the particles have a higher average kinetic energy. Now what that means overall is, where here in the first case we said that the energy transferred from the can to the air was equal to the energy from the air to the can, in this case what I can write down is this, that the energy from can to air is actually going to be much less than the energy from the air to the can. So this is not thermal equilibrium, because there's a lot more energy being transferred from the air to the can than there is energy being transferred from the can back to the air, because on average those particles in the air have a lot more kinetic energy. So what we can do here is write that the can is heated. Maybe we'll underline that word just to show that that's really, really important. This is what heating is. It's where, on average, energy is being transferred from the air to the can. Therefore, the can is being heated. And likewise, we can say that air is cooled. And this is exactly what we mean by cooled, is that on average, overall, kinetic energy is being transferred from the particles in the air to the can. That's why we say it's being cooled. And students might say, well, hang on, does this mean that the room is getting colder whenever I take a can of Coke out of the fridge? Well, the fact is, yes, it is. But what's worth emphasizing to your students is that because the can is so small relative to the mass of air in the room, you don't really notice that difference. But if you were to take loads and loads and loads of big, bulky, very cold objects out of a fridge or a freezer and put them into a room, you probably would notice the temperature of the room decrease. So that's what's going on here, and this is the kind of thing that we want them to explain. Now, the final thing that you might want to illustrate, because later on I think it's really important that we address the kind of misconceptions that arise around this. You might want to draw some diagrams like this, because a student might say, well, hang on, sir, hang on. So you're saying that when I take the can of Coke out, what's happening here is energy is going from the air into the can. But that doesn't make sense, because what we feel is this. And they might ask you a question, but I'm going to draw a diagram which might preempt this. So what we feel is this. They might say, well, hang on, if I have a can of Coke there that's out in the room, and I put my hand nearby, a bit of a strange hand, but anyway, you get the idea. And I put my hand nearby, what I feel is this kind of coldness moving from the can towards my hand. Just realised I'm off camera. What I feel is this coldness moving from my from the can to my hand. And this is a huge misconception, one of the most fundamental misconceptions in the whole of physics that we need to really address here in Year 7. And what you need to say to your students is, no, this is not what's happening, because during heating and cooling, energy is always being transferred from the warmer object, the object at a higher temperature, to the cooler object, the object at a lower temperature. So what's actually happening, and let's write that down here, what actually happens is this. And again, your diagrams from above should illustrate this, but I think it's worth doing these extra little diagrams just to make the point crystal clear. What's actually happening is this, that when you hold your hand up like this, you could tell them that your, sorry for my awful diagrams, you could tell them that your body temperature is actually around 36.9, let's say, 36.9. Apologies, my pen's not working. 0.9 degrees C. 36.9 degrees C. So what's happening here is that the air around your hand is going to be heated. The particles are going to end up with more kinetic energy, and that's actually going to cause the cold can of Coke to receive some thermal energy from your hand. So what's actually happening is thermal energy is going this way from your hand towards the Coke. And what you want to stress to students is that feeling of coldness in our skin, our hand or whatever, when we put our hand near a can of Coke, or when we open the fridge door, or we put it near an open window on a cold day, whatever, that feeling of coldness, which we experience as coldness coming towards us, is actually thermal energy being transferred back to the cold object. And it's really, really important that we emphasize that, and you'll see that there are lots of questions that address that idea in the slides. And the last message that I would give to you, and I think this is a good catchphrase that you want to repeat to your students again and again and again, just to get rid of that misconception, is that there is no such thing as coldness. This picture does not happen. There is no such thing as coldness. In the next lesson, we will start to look at the different ways that heat can be transferred, the first one of which is conduction.